Hello everyone, my name is Okeke. I'll be presenting a paper titled Dynamic Response Characteristics of an Automotive Lamp Assembly. Background: premature fatigue failure of automotive lamps presents a big challenge in the design of automotive lamps. The modern automotive lamp assembly has complex geometry and is constructed with different components of polymer materials. The assembly is normally designed with the gap between parts being very small. With each part of the assembly having different geometry and material, they are expected to respond differently under dynamic loading. Understanding the dynamic behavior of the lamp is crucial in designing a product that meets the consumer vibration specification. Objective: in order to validate the dynamic response of an automotive lamp assembly, the following tasks are carried out. Measure model properties of the lamp assembly using laser scanning vibrometer. Use vibration shaker to measure harmonic response to the lamp assembly. Perform numerical model analysis and validate the result with experimental data. Numerically obtain harmonic response of the lamp assembly and validate the result with the experimental data. Dynamic response analysis. Model analysis and harmonic response analysis are key in characterizing the dynamic behavior of a system. Model analysis. The theory governing model analysis is given. The two most important parameters in model analysis are mode shapes and corresponding natural frequencies. Harmonic analysis. The theory governing sinusoidal harmonic response is given. Model geometry. Here, we designed the lamp geometry using CATIA V5. It is a simplified assembly constructed with three different polymer materials. Housing is made of PPT40. Bezel and outer lens are made of PC. Optical lens is made of PMMA. And we also have heatsink, which is made with steel. This lamp assembly is manufactured and used in experimental testing. Experimental model response. The test performed at Polytech using vibration shaker LDS V201 and Polytech PSV 500 extra scanning head. The lamp was suspended above the ground using an elastic cord, basically to form a free arrangement. The lamp was excited from 10 to 1000 Hz frequency, and the response characteristics were measured with Polytech PSV 500 extra scanning head. 3 scanning heads were used to capture the complex 3-dimension of the lamp assembly. So, looking at the image below, you can see that you can see the 3 scanning heads used, and also the force gauge and vibration shaker and the lamp, suspended lamp. Experiment: harmonic analysis. Harmonic analysis test was performed under the room temperature using LDS V721 vibration shaker. The shaker was driven by LDS 5K VS power amplifier and controlled with LDS laser USB controller. The lamp mounted on a test fixture was excited from 10 to 1000 Hz frequency along the lateral direction using a sine sweep input of 1G. The response was measured with a PCB miniature accelerometer. Results: mode shapes validation. Here we have experimental mode shapes and simulation, the one obtained using simulation. The experimental mode shape, as we can see, all the 4 mode shapes obtained using the experiment are in good agreement with the simulation mode shapes. Harmonic response validation. The harmonic response of all the components of the lamp assembly is obtained. Here we have harmonic response for housing, bezel, optical lens and outer lens. You can see that from 10 to 230 Hz frequency, the experimental response is in agreement with the simulation. And in fact, that region covers first three resonances, which are very important. Harmonic response with corresponding mode shapes. Here we have harmonic response and corresponding mode shapes, the first three harmonic responses. The first mode shape shows that the whole assembly is under bending condition, rotating about the upper and lower left lamp mounting brackets. The second mode shape also shows that the assembly is under bending mode, moving along lateral direction. For the third mode shape, there is combination of tensile stroke compression and bending modes. The assembly is moving with respect to longitudinal direction. The mode shapes clearly showed that we are dealing with bending related problem. Conclusion. The experimental mode shapes and corresponding frequencies were in good agreement with data obtained numerically. The experimental and numerical transmissibility curves compared well up to 230 Hz frequency. The lamp's first three modes deformational patterns clearly showed that the assembly was vibrating under bending mode. These modal and harmonic results are important in fine-tuning design and also in predicting the fatigue life of a lamp assembly. Thank you. And if you have any question, please get in touch. Thank you.